Come on. Biggest issue is when they moved to the 3rd edition, they changed the numbering of the chapters, and now my chapter numbers don't align very well. So what I believe are chapter 15 and 16 might be chapter 16 and 17. I genuinely don't know off the top of my head. So in my lingo, chapter 15 is UV spectra, technically UV vis, and IR. Chapter 16 is mass spec, and then I'm just going to say NMR, because the NMR can split out to carbon or hydrogen, technically and hydrogen. Okay, so just as kind of a layer of potential clarification behind those. Does that make sense? Okay, so summary for chapter 15. UV vis. Okay, UV vis as a form of spectroscopy uses ultraviolet light or visible light. Okay, technically both. And what happens is we just scan the structure, or we scan a sample. You've done this before, believe it or not. Okay, remember you did Beer's law? Vaguely remember Beer's law? Okay, that's UV vis spectroscopy. Okay, it's effectively the same thing. Okay, what's the other one I'm thinking? Atomic line spectra. So I know there's an image of it in the 130 room. I don't think there's one for our other lecture rooms. But like if we looked at a hydrogen sample, we hit it with 20,000 volts, it comes out and it spits out a spectrum. And we see these colored lines, right? Of course I drew them out of order, but let's not worry about my color issues. Does that make sense? You remember that? Okay. What caused those colored lines? Electrons. What about the electrons? Electrons moving between different orbitals, sort of. Those lines aren't just electrons moving between orbitals. It's very specifically the electrons moving down orbitals. Okay, going from a higher energy state to a lower energy state, which is why we see the light emission. Okay, the thing that was so cool about this is that we see lines. Whereas if you look at, use a spectroscope or just a prism with natural sunlight, you don't see lines of color. You see a full spectrum. Okay, you see a continuous spectrum. Why did we not see a continuous spectrum? Well, that's because the electrons are dropping to specific energy levels. That's where we got the idea of energy levels for our individual orbitals. Okay, that's what that all meant. Okay, so when we're talking about UV vis spectroscopy, we spin that on its head. Instead of jamming 20,000 volts into our individual sample to get the electrons excited so they can fall back down and look pretty, we instead just shine light on the sample. But that light passes through a monochrome, a filter that only hits you or only allows the passage of a particular wavelength of light. Okay? And so what ends up happening is we scan our sample. I think ours might go as low as 300. But we go from 300 nanometers up to about 800 nanometers. Okay? 300 to 400 is our UV range. Come on, pen. UV. And then the rest of this is our visible spectrum, where we get red, where we get purple, right? Orange, yellow, green, blue, indigo. Does that say pig? No, sorry. It's the first time I've seen it that way. Make sense? Okay, so all we're doing is now shining that particular wavelength of light at our sample. And what we start to do is monitor, does the light pass through the sample? Okay, so what we're trying to do is quantify how much light is absorbed by the sample within it. So what we end up seeing is usually just kind of a flat line, and then we'll see peaks and hills, and sometimes you'll see broad spectrum things. Maybe you see sharp peaks, that kind of stuff. Okay? And what those peaks now are referring to as we drew them, so our peaks in this case are up here at the top, are the, technically it's the energy, our wavelength, where light was absorbed by the sample. Okay, so our y-axis is usually absorbance. Kind of, sort of? So for this to work, our sample has to just absorb a particular energy of light. That particular energy of light has to match the orbital jumps available to our electrons. Okay? So if I looked at a compound of, say, methane, would I expect to see the orbital jumps for a hydrogen atom and a carbon atom? Seems reasonable, but we don't. We don't see those at all. Why not? We don't have any atomic orbitals. So I'm not going to look at the spectrum for a hydrogen atom or a carbon atom because there are no longer hydrogen atoms and carbon atoms. It's now a molecule. Okay? That means all of those orbitals have changed, which is why we have molecular orbital theory. And we talk about hybridization. The hybridization already got rid of your s and p orbitals. Those are now all gone. They're turned into sp hybrid orbitals. So the entire energetic system changes pretty drastically when we move into molecules. Okay? But what we could go through and do is now start to quantify. Okay, we shine our light at the sample and we see what we see. Okay? It turns out we don't see much of anything. Okay? So we go through and we start putting more and more things in this. Okay? Because we would presume if at the atomic level, if we get spectra, shouldn't we get spectra when we move to the molecular level? That makes sense. Okay? So what we're doing is just testing to see where the system can come about. And eventually what we notice is that when we introduce double bonds, all of a sudden, we now start seeing peaks. We now start seeing signals appear in our spectrum. Okay, so what would that suggest to you?
There's a movement of electrons.
We now have a movement of electrons. Okay? And in particular, the electrons are now allowed to jump in an energy that corresponds to these wavelengths listed out here. Okay? And that energy happens to match for a double bond. Well, do we have double bonds? Okay, cool, yes, we absolutely have double bonds. Mike, stop being an idiot. Go back to Unit 1, rewatch the lectures. No, we do not have double bonds. What do we have? We have sigma and pi bonds. We don't have double bonds. Okay? Why does that become important to us? Well, if we were to look at an energy diagram, okay, for the connection between the carbon-carbon, quote-unquote, double bond, we would note that we had a sigma interaction, a pi interaction, a pi antibonding, and a sigma antibonding. That looks familiar. That was exam 1. Why would it be relevant to talk about it in exam 1? Well, if we move into exam 2 and we now talk about UV vis spectroscopy, we're caring about electrons jumping. Have I defined any electrons? Nope. So how many electrons should I draw into my diagram? Well, how many electrons are we discussing? We're looking at the connections between those two carbon atoms. How many electrons are in the connection between those two carbon atoms? 4. I've got 2 lines. So I can do 1, 2, 3, 4. Okay, and we can add the arrows on them. For the sake of this, it's not that big of a deal. Okay, I don't think we'll ever encounter a system in this class or second semester where we really need to talk about the directionality of the spin states. Okay, and now what happens? Well, ultraviolet light or visible light comes in, impacts our electron, causes the electron to jump to a higher energy state. That was the absorption of the energy. So ta-da, it's now at a higher energy state. What could it now do? It could fall back down and potentially emit light. Okay? The emission of light becomes a very tricky thing to deal with. Okay? It requires certain circumstances are satisfied and fit, and generally speaking, most things do not emit light, okay, when they're in their excited state. How do we know this? Look around. When you turn off the lights, how many things start glowing? Okay? You're like, well, you're not exciting it with enough energy. How about a black light? Oh, cool, we go to a black light party. Are all colors glowing in a black light party? No, okay, again, the emission of that light is a rare occurrence. It doesn't typically happen. We can release that energy through other forms of vibrations, heat, other issues. Okay? Again, we don't care for this sake. All we care about is that our electron jumped. The energy it took to make that jump is the light or the wavelength of the light that I put in. Okay, so this is my light excitation. Okay? And that's it. That's UV vis. Okay, well, it cares about pi bonds. Do we know anything special about pi bonds? They can resonate. Okay, so cool. Now that we know pi bonds are involved in this, what happens if I string together a couple of pi bonds? How is that now going to change my system? Okay, that now becomes a little bit of a harder question and a little bit more complex. Okay, so what we're going to do is take a step back because we need to simplify some stuff before we can make it more complex. The first thing we want to simplify, when we drew out the molecular orbitals, we looked at the sigma and the pi. Did the sigma do anything? No, which means don't worry about the sigma. All we care about are the pi electrons. Okay? Which for our first system, our black structure, if you will, there was only one pi bond. So if we simplified this out for our black structure, we could switch this all the way now to the system where we had a pi, we had our pi star, and we had our two electrons. What cartoony did this look like? That was a weird description. Work with me. What orbitals did I use to make the pi? To make the pi, what orbitals did I use? SP. No. Because SP orbitals are S-type, which means they make sigma bonds. This is a pi bond. There's no S-type. We just use P. How many P's did I use?
2.
I use P and P, also known as PP. It's been a long week.
It's Tuesday.
Don't remind me. We have a node within each p orbital. That node is relevant because what does it mean at the node? It's a change in phase. How do we represent our change in phase? We represent it with shading. So when we look at this, we could bring those two p orbitals near each other in such a way that they overlapped constructively. That would create a bonding type orbital where it's lower in energy. We could also have interacted them in a way where it was shaded differently, and now what have we created? A second node. So as we go up in energy, we add nodes. Okay? The energy gap is defined between those. Everything good so far? Okay. What happens when we now add an extra pi bond? And actually, let's switch this up. What happens if I add that extra pi bond? Do those pi bonds talk to each other?
No.
No. Which means effectively, all I've got in this scenario is two independent pi bonds with the exact same energy difference between those orbitals. That's it. Okay? So at best, what we would see is a change in intensity of the signal, but we're not going to see a change in the energy because it's the same energy. Good? What happens if I delete that carbon and I now create this system? Now what goes on? Well, I've got the P from that first one. I got the P from that one. Technically, I have the P's from those. P to the 4. Don't do that. Sorry, never mind. Don't do that. Bad wording. Can those P orbitals talk to each other? Yes. And because they can now talk to each other, this is not 4 independent P orbitals. They must communicate. Which means I'm looking at 4 P orbitals all aligning next to each other in a way that they could potentially communicate. Okay? Let's pull back to some molecular orbital stuff. This would represent one of my pi bonds, my pi molecular orbitals. Okay? But if I bring in 4 atomic orbitals, how many molecular orbitals must I make? It's 4. Okay? We can't create or destroy matter. This is more like create or destroy energy. Okay? So if I'm going to bring in 4 different energies, I need to end with 4 different energies, which means the output here, I'm going to have 4 pi interactions. Okay? The spacing between those was entirely unintentional. We could call this pi 1, pi 2, pi 3, and pi 4. So don't worry about the spacing, but we've got those 4 pi systems. Okay? We can add to this. For every bonding interaction, we have antibonding. So for that bonding 1, I also have antibonding 4. For that bonding 2, I have antibonding 3. Okay? And we're going to get fancy with the pictures in a second and dealing with what those molecular orbitals would actually look like with all the orbital diagram, but we don't need to stress about that yet. Okay? We now have our molecular orbitals. Okay? To understand UV vis, what we now have to do is talk about electrons, which means I need electrons in these orbitals. How many electrons should I draw in? If you're coming to 8, that's reasonable. What you've done is counted all the lines in between those carbons and recognize that each line, we'll call them in blue, happens to represent a pair of electrons, and that's 8 electrons. So should we be drawing 8 electrons? No. We drew 4 electrons the first time because we included what? The sigma bond. Am I talking about the sigma bond anymore? No, all I care about is the pi bond, which means I only care about one of those lines. Okay, in each of those systems, which means how many electrons? 4. So now I go through, I can populate. I'll get 1, 2, and then I move up in energy, 3, 4. Why do I have to go up in energy to put in the next 2? I can only fit 2 electrons per orbital. Okay? Why did I not immediately put 1? Why did I not go like this? 1 in pi 2, 1 in pi 3. Say again? Yes, it does require energy to put it higher. Okay, this goes back to one of those named rules when you dealt with electron configurations in 151. I don't remember which one it is. I mean, there's Hund, there's Pauli. Pauli, I think, is 2 orbitals. It might be Hund's rule. Lowest energy. You always put your electrons in the lowest energy. That's where we start. Okay? Which is effectively the same thing that you're saying, just in a slightly different way. Okay? So we now have our molecular orbital diagram for this system. Right? Just like with the first one, we're talking about electrons making a jump. I'm talking about electrons going from where they're populated to where they're unpopulated. So I'm talking about electrons making this jump. That jump is now going to correspond to an energy, and that energy I'm going to see as a signal within my UV vis. What about this jump? What could you tell me about the blue jump versus the red jump? Say again? So the intensity has to do effectively with concentration. That's our Beer's law stuff. We're not changing the concentration. It's still the same number of orbitals, so I would argue there's no intensity change.
I mean, you're skipping a whole orbital, right? Wouldn't that make little no sense?
Why would it make less sense?
Because it would have to follow up on being a pi 2 orbital. If you wanted a, I guess.
Do I have electrons in the pi 1? Yes. Do I have space in the pi 3? Yes.
But
To make that jump, what must happen?
a lot of energy.
A photon must come in and hit the pi 1. But it can't hit the pi 2. Is the pi 2 in front of the pi 1?
Yes.
Yeah. Okay. So the pi 1 effectively gets a shield. So it doesn't make as much sense to be able to pull this off. Could it still happen? Yes. Okay, so this could now push to the intensity. Because the pi 1 has a shield, it's less likely to be absorbed, which means I'm less likely to see it. The intensity is actually going to drop. But you did mention bigger, and I like bigger, just wrong description. Okay? The proper description isn't referencing the intensity of the signal, it's representing how much energy it's going to take for that transition. That energy is a significantly larger jump in energy, and if we increase the energy enough, are we in ultraviolet visible light? No. We transition out of the spectrum and it's no longer visible to us. Or no longer, I shouldn't say visible, no longer detectable to us using that instrument. Okay? So this instrument only really zeroes in on that UV to visible range. Okay? And it just so happens that UV to visible range happens to align with pi bonds. Okay? So when we're talking about UV vis, it's almost exclusively pi bonds and that's it. Pi bonds bring in this added complication of resonance. Well, how is the resonance going to change the system? Okay? This is where we could go through and make you do a bunch of technology stuff, use computer programs to model and be like, oh, the energy of these orbitals is yada, 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 and play around with that and be like, oh. Or we could just go through and say, guess what happens when you add resonance? This gap, that delta, is smaller than the delta on the other side. So the difference for the red is smaller than the difference for the orange. Why is that a big deal? If that gap gets smaller, what does that mean happens to my signal? Okay? Simplest level, it changes. It's going to have to shift somewhere on our spectrum. Okay? If it becomes smaller, where does it shift to? Does it shift to larger numbers or smaller numbers? Good pause on that because that was insanely misleading. Okay? It depends what your axis is labeled. Okay? If it was labeled energy, I would expect the red one to go to a smaller number. Okay? It's not labeled energy, it's labeled something else. What's it labeled? Wavelength. So now I have to consider, well, what's going to happen with wavelength? Okay? If I get a smaller jump, what does that mean for my wavelength? It gets longer. Okay? Yay, how do we know it gets longer? I think that's the proper formula. Okay? Energy and wavelength are inversely proportional, so that's how we're seeing that shift. Okay? So what does this mean for us? Well, this means if I have resonance, what I would expect is my signal to shift to larger numbers. Okay, my primary absorption. Okay, I could have secondary absorptions, pi 2 to pi 4. Okay, that's a larger jump. That's harder to manage and harder to pull off, but I'm going to have lower intensity. The most common jump that I'm going to see is the one that's the easiest for me to pull off. Okay, that's going to be what I would reference as my lambda max. So that gap is now my lambda max. Okay, whereas the gap on the other side is still also a lambda max, but it's now corresponding to a different energy gap. Kind of, sort of? Okay. What we then played around with was, well, what if I have more pi bonds and more pi bonds and more pi bonds? And what we start to note as the increase in pi bonds happens, the closer this gap comes. Okay? So more resonance, I should not write it really small. That's a big summary thing. More resonance equals longer wavelength, or rather longer lambda max. What does less resonance mean? Shorter lambda max. And in, well, I'll give myself 25 minutes because I started a little bit late. You have half of chapter 15. That's UV-vis spectroscopy. Okay? We do push on it a little bit more, but really all we're doing is tying it back to the content that we already addressed with molecular orbitals. So we ready for that one? Because we love molecular orbitals so much, right? Yay! Yeah, that's where you up and down. Okay, I guess I'll just turn my head for a while the rest of you shake, right? Changes the orientation of your head shaking. Okay? Let's take a look at our molecular orbitals. What does the picture look like? Okay. Well, pi 1, this is the lowest energy. Lowest energy means what about the shading? And really about the phase is the more important reference. They are all in the same phase. And I'll switch to green just for the sake of it. Okay. They are all aligned. My electrons can jump all the way back and forth. An electron in this orbital can go anywhere the hell it wants. Okay? That's a very stabilizing feature because it can go back and forth. That's why it's the lowest energy. Okay? As we go up in energy, what happens to the number of nodes? They also increase. So if I start at this pi 1 as being 0 or 1, depending on how you want to call it. Why do we want to do it that way? Why 0? They're all in a constructive overlap, so we could just say there's no node. Or we could call it 1. There is a node running right through the dead center of all of them. Okay? But no matter what, when I'm looking at these p orbitals, will I have that node? Yeah. Which is why we can call it 0 nodes for that first one. So it's going to depend on your perspective and what you're trying to deal with. As we go up in energy, what has to happen? Well, I need an extra node. Okay? So how can I go through and shade these so that I get one extra node? Does this generate one extra node? Yeah, technically it does. Okay? When we talk about the molecular orbitals, though, we always push for symmetry. Okay? So while this does technically show it, it doesn't represent the symmetry well, and we need to deal with symmetry. Why is symmetry so important? Go back, look at your ionization energies in 151. Okay? There were trends with that, and there were things that went against the trend. Why did they go against the trend? Symmetry. Symmetry plays a really important role in virtually everything we deal with. Have you seen those studies where they talk about the most attractive person? Why are they attractive?
Symmetry.
Symmetry. Okay? Symmetry plays a very important role in virtually everything that we deal with. And depending on where you go within organic chemistry, you can see that symmetry effect manifest as a larger and more prevalent thing. So the most symmetric way to get one node would be to introduce it there. As I go up in energy, what do I need to do? I need more nodes. How many more nodes do I need? I need a total of 2. How can I do it? One node, 2 nodes. As I go up in energy, I didn't draw that one in an appropriate spot. Here, can I slide them? Sometimes technology works with me. That worked out kind of. I can go through and I can do my last, molecular orbital. And what's going to happen here? I get even more nodes. Okay, it's the highest energy. It's going to be the one where every orbital doesn't communicate with every other orbital. That does not allow the electron to pass through. That now becomes an anti-bonding orbital. And what we've now drawn out are the molecular orbitals for that butene, butadiene structure. Okay? We've also drawn on our electrons. We talked about the electrons making that jump, so more resonance equals longer lambda max. Okay? We know how to draw our molecular orbitals. All should be great. We have one more piece to add, but before we add that,
I don't know if this might be it, but what's the best vocabulary you can say as a jump to a pi 2 to a pi 3? Is that high?
awesome. So we want to deal with a description for jumping. Okay, you said pi 2 to pi 3. Is this pi 2? And for the sake of people looking at home, and the words got in the way. If we look over to the other system over here, is that pi 2 to pi 3? It's no. Right? That was pi 1 to pi 2. So you could go through and reference very specifically each of those jumps. Okay, that's a bit tedious. We would like a language that represents exactly what's happening. Okay, well, what can you tell me? To make the jump, where does our orbital have to start? What has to be true about that orbital to allow the jump to start?
Has to be filled up in electrons?
Slow that a little bit. Does it have to be full of electrons? No, it just has to have at least one electron. That's it. Okay? For our purposes, it will have 2. Okay? But it just has to have 1. Okay? So I need an orbital that contains electrons. Okay? So I could call it an electron-containing orbital. That's an awful lot of words, but we could drop that down to ECO, right? That's not bad. Echo? We can get away with that. Okay? But is it all echoes? Does the pi 1 have a jump in our first or our second diagram? No. So I need to be able to differentiate not just that it contains electrons, but also recognize something about the energy levels of said orbitals. Okay? And for the record, echo is a horrible name for this. Okay? So someone went through and tried to describe what these are. So first and foremost, we're talking about molecular orbitals. Okay. Where does it start? It has to start at an occupied molecular orbital. Okay. But not any occupied molecular orbital. It must be the molecular orbital that is highest in energy. So instead of naming the orbitals that are doing the jump, which is not going to be consistent, I can now say I'm jumping from the highest occupied molecular orbital. Even that's a mouthful, so what do we switch it to? HOMO, our highest occupied molecular orbital. Where are electrons jumping to? Well, they're jumping to an orbital that is unoccupied, and it must be the lowest energy. And if we now process all of that, that makes this orbital our lowest unoccupied U molecular orbital. So what we're talking about with UV vis spectroscopy is how do we transition from the HOMO to the LUMO. That's it. Okay? That's going to correspond to a lambda max. That lambda max is dependent on the resonance of your structure.
Since the LUMO is less stable, is it higher in energy than the HOMO? Orbital.
Yes.
But we just call it lowest unoccupied.
What's the lowest in reference to? It needs to be unoccupied so the electron can make the jump. But I'm not going to pi 4. Okay. So the highest was to differentiate pi 2 away from pi 1. The lowest is to differentiate pi 3 away from pi 4.
Okay. But as we increase in bond
Pi 3 is absolutely higher in energy than pi 2.
Okay.
And we could see that with the increase in the number of nodes. More nodes, higher energy. This is why we talk about molecular orbitals early on, so that we can address what's happening with these as molecular orbitals. It's now kind of the next tier beyond it. Okay? Guess where we start second semester? Molecular orbitals again. Okay? How badly do we start it? I had a student come into second semester OChem, sat through the very first class, came up after class and was like, I have no idea what a molecular orbital is. Should I drop? I said, no, don't drop. Stick it out. We'll work through it and put it all together. He's probably one of the best organic students I've ever had. Okay? So he's coming from a background of zero molecular orbital understanding and is now, he's one of the jerks now doing molecular orbital calculation stuff. I'm like, why? Why do you really need that? Oh, I understand why. It's what he's working on. Okay? So you don't have to be an expert here. This starts you off down a path where you could potentially dig into it if you wanted that path. If you don't need to worry about it. Don't stress. You just got to make it through. Molecular orbitals are not going to haunt you through medicine, I think. I genuinely don't know. I haven't done a whole lot of medicine. I would hope not. Does that help you with UV Vis? You happy with that? As happy as you can be?
I mean, it's just like the wording on chapter. I barely look into this, but I was just like, oh, did we learn this? In which I recognize all this. It's just like maybe the wording was a little weird on the spec or the smart word that maybe.
That's possible.
Yeah.
Yeah, I'd have to double back to look at that.
So when it talks about like conjugation, is it like the same?
Oh, that's a fun one. What is conjugation?
Well, it's something like this. It's
Okay. It's sigma pi. That's conjugation. Why do we care about conjugation? What is special about this? It's resonance. So conjugation is just another way of talking about resonance. Okay. Why use conjugation instead of resonance? Probably has to do with the articles of speech and nouns, verbs, adverbs. That's probably what's going on and why they have to introduce conjugation as opposed to resonance. I think resonance is going to be a noun and conjugation is going to be an adjective. Go back and take English 101 again. I could easily be wrong on that, but that's my guess is what it is. I don't think it's the other way around. Whatever, in any case. So, we good with UV Vis? Okay. when you encounter other language, it's going to happen. There's lots of different ways to describe things. So if you're seeing a word that you're just like, what the hell does that mean? What should you do? Look it up. Okay? And if you don't want to look it up, that's also acceptable. What else could you do? Ask, send me an email. What the hell is conjugation, Mike? Oh, no, that's just what this is. This is the same thing you've already looked at. We're just using a different word to describe it. Okay? Effectively, nomenclature. And as we already learned with nomenclature, there's not one word to describe anything. So you've got to be kind of familiar bouncing around with those different languages. Do we need to do IR? Is that a yes, do IR?
No.
No, that's okay.
The 13 carbon NMR thing does come on a lot on chapter 16 smart work. Like all my questions have to do with that one.
Yeah.
Yeah.
And it's all coming back to the exact same thing with that. So what I can do, well, actually, let's not even do that. Let's go back to this. So we're good with UV Viz? Okay, and you're just complaining about the language? That was really all the issue. So I went through and talked about chapter 15 for nothing.
Did everyone else know?
Oh my god.
You eat this? Like, no?
Okay. I doubt it. No one else probably was brave enough to ask, so that's okay. IR, I would argue there's nothing for me to really draw. It's effectively the same principle, except instead of looking at ultraviolet and visible light, you're using infrared light. Infrared light is an even longer wavelength, and it's such a long wavelength that it's not enough energy to cause electrons to jump orbitals. But it is enough energy to cause electrons to, or not really electrons, the bonds to shake. All they do is move. Okay? So you're now, instead of looking at the energy levels for electrons to jump, you're looking at the energy levels to cause a bond to vibrate. Okay? So it pushes back to what bonds are. They're really just springs. And it's how does that bond vibrate? That corresponds to a signal within your spectrum. Okay? In UV Viz, you're not quantifying it really. You're just saying, oh, more resonance, longer number. Less resonance, shorter, smaller number. Okay? In IR, you now look at the shape of those signals and say, that means I have this bond. That means I have this bond. Once you know all the bonds, what can you do? You could piece bonds together to make functional groups. Okay? So this is a pet peeve that I think comes across in the videos. IR does not tell you functional groups. IR tells you bonds. Okay? So when you go through and do your analysis for IR, analyze it based off of bonds. If you have multiple bonds, you can now start answering the question, do I have certain functional groups? Okay? The biggest pet peeve, because everybody does it, I drew it way too nice looking, but if we saw something like that at 3,000, we'll go ahead and call that 3,400 to give an idea of breadth on this. We'll call that 2,500. Okay? That's way outside the matching of a standard CH stretch. Okay? But it does happen to match an OH stretch. Okay? But if you look up this OH stretch, you will typically see it labeled as C2, whoops, not C2, as CO2H. Okay? And what they're trying to say is that this is characteristic for a carboxylic acid. But they aren't saying that. They're saying the signal is that bond. That's all they're saying. But if you see it shifted to such a low number, that would suggest that that OH bond is close to something that's further polarizing it, weakening that bond. Weakening the bond causes a shift in the signal, and that's why it shows up lower. So there's a whole bunch of extra steps behind that logic. And instead we go, oh, that's a carboxylic acid. No, it's an OH. That OH is shifted to lower frequencies because it is a weaker bond. It is a weaker bond because it is close to a carbonyl. How do I know I have a carboxylic acid? I better freaking find the carbonyl in my spectrum. Because if I don't see that carbon-oxygen double bond, that ain't a carboxylic acid. That's something else. Okay? So you have to be able to process all of those individual steps. Okay? Again, uber pet peeve on this one because everybody screams carboxylic acid at that. Okay? The rest of it is just shape matching. Look at a bunch of spectra. Okay, this is where you should be using your textbook or going to the internet and just looking at spectra of compounds. Get a feeling for what each of those shapes represent, because that's all it is. Shape matching. Carbon NMR. And actually what I'm going to do is erase the C for the moment. When we look at NMR, what are the things we look for?
The peaks.
What do you mean the peaks? Elaborate.
How many there are, depending on each NMR,
How many peaks?
1 and 2.
Okay. This is why I want clarity behind this. Okay. If you go through and look at this and call this 2 peaks, I would agree with you, except that looks an awful lot like 7 peaks, right? Okay. So it's going to come down to your interpretation of what peaks are. As long as you're good on it, it's actually not going to matter. Okay. Because the only way that would matter is in a conversation. And really that conversation is only happening from me to you. Right? So what I would argue is not calling it peaks. I would say it's the number of signals, where signals is now a larger or broader category. Right? What comes after the number of signals? Now what we would do is move to chemical shift. Did a crap job color coding for the record. Okay? Chemical shift tells us about the local environment. What's local? Literally, what is it connected to? Okay? And if you're wondering about what it is, not yet. Okay? What comes next? Integration. Okay. Integration gives you the ratio of different its. Like I said, we're going to come back to it in environment, or it in a second. What's the last thing? Multiplicity, which is now talking about neighbors affecting the signal. And because they're affecting the signal, what happens? Your signal splits into okay? This is NMR. Okay? Depending on where you're at within your skill set, you will be addressing all of these or only some of these. Okay? Within that skill set, if you're weak with NMR, you're potentially just addressing 1 and 2. Arguably, everybody should be getting into integration. Multiplicity is a whole nother beast. Trust what you get to. Okay? Kind of, sort of? So what is the it? NMR is nuclear magnetic resonance. Okay? So we're talking about magnets, and we're talking about nuclei acting as magnets. Okay? I don't understand enough about the theory to explain why, but only certain nuclei are magnetic. Okay? That magnetism has to do with the balance of protons and neutrons in the nucleus. Okay? So if that balance gets out of whack, it's no longer magnetic. There are lots of elements. In fact, and I'm probably wrong, but let's just say all of our elements can be magnetic. Okay? So we could go through and make every single element magnetic as an individual nuclei, so that we could potentially detect it. Okay. The problem becomes that it's unstable. We're talking about the balance of protons and neutrons, and when you mess with the balance of protons and neutrons, what happens? Kabooey! That's called atomic bombs. You're messing with the balance of protons and neutrons within a nucleus, and that's where you get radioactive decay. Okay? So when we go through and deal with this, the next kind of part is, while we can make all of these potential elements have magnetic nuclei, it's not just a question about making them all have a magnetic nuclei. I now have to make enough of that to turn it into a molecule, and now enough molecules that can be detected by the instrument. So if I'm trying to really zero in, that becomes really painstakingly painful to go through and process. Does that make sense? So instead of us building a bunch of isotopes, what we rely on is nature. And we say, what does nature have for us that we could use? Right? And a couple things come out of it. Number one, hydrogen. Simple little hydrogen with one proton is magnetic. Okay? And that's really special to us. Because what is the natural abundance of hydrogen for the element of hydrogen?
It's almost 1-1.
1 to 1 is not, that would be a 50%.
Oh, it's like 99.
Yeah, there you go. It's almost 1 exactly. Okay? When we look at the abundance of the different isotopes of hydrogen, hydrogen 1 makes up 99.999% of all isotopes. Which means if I make anything that has hydrogen in it, 99% of them are going to be visible to the spectrum or visible to the instrument. That's pretty powerful. Okay? Which means an individual sample has tons of things for my instrument to detect. Okay? I could go through and look at every other single element, but we skip on to what other element? Which one are you having problems with? Carbon. We look at carbon. Okay? And when we go through and look at carbon, it turns out the most common isotope of carbon is carbon 12. And we know it's carbon 12 because the average atomic mass is dang close to 12 because almost all of it is carbon 12. Okay? Carbon 12 is not magnetic. Right? Which means it's invisible to our instrument. We can't see it at all. Okay? But if it has one extra neutron, carbon 13, it is visible. Okay? So I can detect carbon 13 in an individual sample. But since it's not the most abundant, I'm not seeing a lot of carbon in my individual samples. I have to now run the spectrum or run the instrument longer to build up a larger signal-to-noise ratio. Right? Because I have to detect that one carbon-13 away from just random scattering around us. Kind of, sort of? Right? It turns out that carbon-13 does make up a sizable portion. I don't remember the exact percentage. I want to say like 10%. So that if we look at an individual sample, okay, of whatever we've made, about 10% of that sample is visible to the instrument. Right? This is why carbon-13 takes longer, because it's a very small concentration. So I have to run it a whole bunch. Okay? But that also is magnetic. There are lots of other isotopes out there that are magnetic. Phosphorus has one, sulfur has one. Right? And in fact, when we bought our instrument, they were like, oh, do you want to have phosphorus abilities? And I was like, no, we're barely going to use hydrogen and carbon. Don't upsell me on something else, okay, that we'll never use. Okay? So you can test a whole bunch of other different isotopes. It just requires that you change how you're visualizing it and all that fun jazz. Make sense? Okay? So the it is either hydrogen or carbon, which is why when you look at the chapter on this topic, you get hydrogen NMR and carbon NMR. Okay? You'll note here, I just went through, they're the same thing, because really they are. And if we go through and look at the difference between carbon and hydrogen, I will go through and I will find that hydrogen and carbon are going to produce signals. So the number of signals I see is relevant for both hydrogen and carbon. Okay? Chemical shift, where do those signals appear, is also relevant for both carbon and hydrogen. Integration now becomes questionable. It's the ratio of the individual types of hydrogen or carbon in our spectrum. Why would that be problematic to run for carbon?
Doesn't carbon 13?
What about carbon 13?
It's going to show up more than
It's going to show up less for our integration. We see much less of the carbon in there, which means am I able to guarantee for an individual sample that I have at least one carbon for every single other carbon? No. Which means the integration ratio for my carbon structure becomes very questionable. It comes down to random shifting of balances of the carbons in there. I'm not going to be able to establish a fair ratio. Hydrogen, I can, because 99.99% of it is there. Right? So if I look at 10,000 hydrogens, almost all of them, and I can do the math later, okay, are going to be magnetically available, and I can see them in my spectrum. So I can create a fair ratio. Does that make sense? Which means when I look to the integration, really all I'm going to see is hydrogen NMR being relevant. What happens when we move to multiplicity? The multiplicity has to do with neighbors affecting the signal. What are the neighbors? What is a characteristic of the neighbor? The neighbor must be magnetic. Because if it's not magnetic, it's not going to affect the magnetic signal, and therefore is irrelevant to multiplicity. So again, when we go through to look at carbon NMR, carbon 13, I can't guarantee that that single carbon that I'm looking at, even if it was carbon 13, that is also guaranteed to be next to another carbon 13. In fact, the odds say it won't be. And if it won't be, I don't get splitting. Which means the multiplicity that I look at is typically just for hydrogen. Anybody know something weird about what I just said? I wasn't listening to you, Mike. I know. That's why I said it. And it makes me sad too. I said typically. What does it mean if I say typically? Not always. Okay? Typically, we only look at hydrogen. Multiplicity is talking about neighbors, and our neighbors must be magnetic. When we talked about hydrogen, it's other hydrogens being magnetic nearby. When I talk about carbons, we talked about other carbons being magnetic nearby. Is there something else that's magnetic nearby next to a carbon? All of the hydrogens are nearby. Could the hydrogens affect the carbon signal? Yes. Okay? So typically when we look at carbon NMR, we ignore multiplicity. Okay? And it's decoupled is what we talk about. So when you're looking at it, I think it's decoupled. A decoupled spectrum, all you're evaluating is carbon, all you're evaluating is hydrogen. But you can couple them so that you can see how hydrogens affect the carbons. Okay? That's only done for carbon NMR, and it's what's known as, I'm probably wrong, but I'm just going to say it anyway, a DEPT spectrum. I don't know what it stands for. Don't ask. Okay? That DEPT now goes through and for an individual carbon says how many hydrogen neighbors do you have. that can be very beneficial. Because if I have a carbon that's at the end of a chain, a methyl group, it has 3 hydrogen neighbors. So if I look at the carbon signal for that, what's going to happen to it? It should split into 4 peaks because it has 3 hydrogen neighbors. So it can give me some more structural information to look at a DEPT spectrum. Okay? This is the first time ever in my 20 years of talking about NMR spectroscopy that I've even mentioned DEPT to a class. Okay? It is not a critical thing to evaluate, so don't stress about it. It does show up in the ACS study guide. It can show up on the ACS exam. It's not critical to evaluate. Okay? Kind of, sort of? Okay. Which then takes us back to your actual question, because eventually I'll get to it. Okay? You cared about carbon NMR. Well, we just listed all the things that were relevant. Okay? We said carbon NMR could get DEPT on us, okay, but it's not going to, which then means all we're going to do is delete everything that was not relevant to us. We don't care about any of those other things, and all we care about is the number of signals and the chemical shift, which means all of the questions you are seeing in SmartWork are based off of those 2 concepts, and that's it. Every single one of them. Okay? And you might be like, well, that's a bit crazy. I'm not quite sure I believe you. Okay? How many carbon signals do you see?
2.
Okay, we have 3 carbons, but we only see 2 because
Those
those
are chemically
are chemically identical. Okay, why? Internal mirror plane. Where do we talk about internal mirror planes? In the chirality chapter. Why do we talk about it there? So that we could deal with it when we dealt with spectroscopy. Okay? We're seeing how those effects can manifest in our later chapters. Remember I said it's all tied? You can't just forget things? Hooray. Right? Chemical shift. It looks familiar, right? It's not that far off. You go, oh my God, this looks like hello. Okay, well, slow it down. What are the number of signals? Oh, I gotta think. Yeah. So there's a carbon. I'm totally running out of colors. There's a carbon. There's a carbon. All 3 of those are unique, right? That one should be different from all the others, but that one's the same. I mean, I got a big color palette. Let's see how this goes. Same. That one's new. Did I do orange? I did orange. Okay, yellow. Why not? It sort of shows up. I'll make it really, really, really yellow so you can see it. Is that noticeably a different pink? That one's... I haven't done black yet, have I? Cool. There's black. Okay? So cool. Those would be all of our unique carbons. So we could go through and now say that we would have a whopping total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 signals. Okay? Cool. So we answered the signal question. What's the chemical shift question? You got 10 signals. Where are each and every single one of those signals going to show up?
very close to each other.
Oh, and there becomes a fun question. Okay? If you go through and evaluate where you would predict each of those, okay, Andrew's making the statement that they should all show up really close to each other. Okay, why should they show up really close to each other?
It's within the, is it the
Good deal.
50 to 100 range?
Okay, so what you've done, which is fantastic, is there was that cheat sheet of what you should memorize for your carbon NMR, right? Okay. And when we look at this, we would say, well, don't all of those fall in that range? No. I mean, those are probably all in that, I think it's 100?
100, 150.
Is it 100?
100 to 150. I'm a little nervous about the triple bond. I don't know where that one shows up. This one here
It's past it.
is past it. That shows up at 200.
That's
This one here shows up at
50.
okay, the 0 to 50 range. Okay? That's what I want you to be able to do on an exam. What do I want you to be able to do in a homework?
Same thing.
More. Okay? I want you to be able to go through and tell me relatively where should all these things fall. Okay? Towards each other. That becomes significantly harder as a question. How should you go through and navigate that question? I'm going to delete it all and see if I can't pull up the question that I would bet you're struggling with. But I won't.
Just how many unique carbons there are.
Yep. So this is now just the number of signals. That's it. So you would go through, this is where you're dealing with mirror images and rotations and all that fun jazz to try and identify how many unique carbons there are. Okay? You kind of already did this in one of the specs quizzes, I think. A little bit shaky on that, but I think a specs quiz pushed towards this concept at least. So what you would do is just go through and do that. Okay? Next one, go away solution. Okay? This question is a little bit different. I'll give you that one. Okay? There are two structural isomers of C3H7 Br. They can be quickly distinguished using carbon NMR. Okay? So this is a slightly different system because now you have to come up with a way to distinguish them. Okay? You're now being asked to think a little bit outside the box. Okay? What you're going to be drawing in here is things that match. I want 3 distinct signals, and I don't know what part 2 is. Maybe it's 2 distinct signals. So you've got a formula. Can you draw a structure from a formula? Yes, you can. You did that in Unit 1. You're now doing it again, but now you're doing it in a system that allows you to try and go through and process this. So I have 3 carbons. I'm just going to start, why not? 3 carbons. Okay, 7 hydrogens. 1, 2, 3, 4, 5, 6, 7. We'll call those all hydrogens. And then I have 1 bromine. Oh, really? Did they really do it that way? Well, that was too nice. They didn't even have a double bond or a ring in there.
That's the thing we did on the first.
It's not the exact spectrum, but right idea. Okay? So cool. What they're saying is there's 2 different ways you can come up with this formula. What did I do? Let's just throw away out there and see what happens. Okay? How many carbons are in this? How many unique carbons?
3.
Okay? For sure the carbon where the bromine's connected has got to be unique from everything else. When we look at the other 2 carbons, are they unique? They're just bonded to hydrogens and carbon. Okay? It's not just necessarily what they're immediately bonded to, it's can you tell a difference between them? Yeah, I can tell a difference. Probably not using orange. That green carbon is closer to the bromine than the red carbon. I will never get the red carbon and the green carbon confused with each other. Why? Because they're chemically distinct. What does this mean? I have a carbon structure, an isomer that matches that formula that has 3 unique carbon signals. Okay, it had 2 parts. They also said there's 2 structural isomers, which means there is another. So how else could I arrange these atoms to set this up?
Put bromine in the middle. And then the hydrogens around the carbons.
And I didn't want to draw the hydrogens, to be honest. So I appreciate that you thought that pause meant I was making fun of you. But no, I didn't want to draw the hydrogens. Okay? Do I need to draw the hydrogens? you don't need to draw the hydrogens. Okay? You only need to draw hydrogens on chiral atoms and double bonds. That's it. Those are the only times you must draw and heteroatoms. You can't imply on heteroatoms. Oxygen, nitrogen, you wouldn't have them on your halogens, but same deal there. How is this going to change my spectra? Do I have 3 unique carbons again? For sure, the middle carbon. But now these outer 2 are the exact same. Because they're the exact same, I only get 2 signals. So this question becomes a little bit harder because it's asking you to draw structures. Don't panic, draw some structures. Right? What's the number one thing I tell you need to do? Draw. Draw it out. Okay? So start committing to that draw out process. That's when you'll see improvement. That's when you'll see breaking through, like, I don't know how to answer this question. Well, just start drawing it and see what happens. Once you get out of the English language and into OChem, it becomes easier. It's when you're hovering on that threshold between which language do I want to answer in that you've got a problem. So commit. With that, we're done.